morning dear students, myself Sachin S. Pawar and I welcome you to my 12th video on Unit 5. In today's lecture we will be discussing liquefaction of gases. Okay, so let's begin with liquefaction of gases. What do you really mean by liquefaction? If I ask you, then liquefaction is nothing but conversion of a gas into liquid. This part is very well learnt by a concept that we have already learnt in our previous sessions. In gas, the particles are at a very random motion due to high thermal energy, and they have lot of empty space in between them. So if you want to convert the gas into liquid, then you need to pressurize the gas particles together, means you require an external pressure, and you need to decrease the thermal motion of those particles. That is, you need to decrease the thermal motion, that is, you need to decrease the temperature. So these two factors have to be decided, and at a proper pressure and temperature the gas is going to liquefy. The gas is going to liquefy. What Andrew did is this: he took different gases in the container, as you can see on the right hand side. For example, carbon dioxide gas is taken. We will learn about carbon dioxide, and using the piston, this piston can be moved inward and outward. So if you move this piston inward, the pressure on the gas increases, and if you move outward, the pressure on the gas decreases. That we have already learnt. That what is done, and whatever experiment he has performed on different gases, he performed it at different temperatures. And based on his observations, whatever observations he got, those observations he analyzed graphically. Graphically in the sense, he plotted the graph of pressure versus volume at different temperatures. And these graphs are known as Andrews curves. These graphs are known as Andrews curves, and the Andrews curve for the carbon dioxide gas at different temperature you can see on your screen. In the beginning it may look difficult for you to understand, but with a proper understanding you will be able to do it. See, what they have done is, we have different curves here at different temperatures: 48.1, 30.98, 13.1, 21.5 and so on. We have different temperatures at which these experiments are performed. Now what is done here? Basically a very simple thing. Okay, basically what is done? He has taken gas in the container, carbon dioxide gas is taken in the container, and he has just manipulated the pressure and volume. When the pressure changes, volume should change. You know, pressure is inversely proportional to volume according to Boyle's law. According to Boyle's law, the pressure should be inversely proportional to volume. We know that already. So he used it. Now see, at different temperatures what is going to happen. You see this curve, the curve at 48.1 degrees Celsius. The curve at 48.1 degrees Celsius. So we'll just see the curve at 48.1 degrees Celsius. See what happens. The curve at 48.1 degrees Celsius, you will see that red color curve, you see what is there. You see that as the at 48.1 degrees Celsius, as the volume decrease, the pressure is increasing, and there is a gradual increase in pressure with decrease in volume. There is a gradual increase in the pressure with decrease in volume. There is a gradual increase in the pressure. That means it is following Boyle's law. It is following Boyle's law, and if it is following Boyle's law, it should show ideal behavior. That is, it should obey ideal gas PV is equal to nRT. But at this temperature, he saw none of the gas particles were liquefied. That is, it is no liquefaction was there in the container at 48.1 degrees Celsius. No liquefaction, but the gases was behaving ideally. It's an ideal gas. They were behaving ideally. Okay. Now he brought down these temperatures. Now from 48.1 degrees Celsius, he brought down the temperature to certain temperatures, and he got certain interesting observations, and that gave him the idea regarding the liquefaction of gas. Let's see. I went to different temperatures. Now here we have 48.1, see 35.5, 32.5, 31.1, 30.98, 21.5, 13.1. So if you see it carefully here, these curves, basically these curves, which one? The curve at 48.1, you will see it is following Boyle's law, because pressure is found to be inversely proportional to volume. Volume is found to be inversely proportional to volume. But if you just observe these, here also liquefaction is not there. At 35.1, 35.5, 32.5, 31.1, liquefaction is not there. So here you will see that Boyle's law is obeyed, but for 30 below 48.1, for example, you see 35.5, here you see a gradual decrease in the pressure will increase the volume, but after certain pressure, you see pressure is increasing, but the volume is not decreasing to that much extent. That means it is deviating from ideal behavior. It is deviating from Boyle's law. It is not following Boyle's law. So here below 48.1 degrees Celsius, deviation from ideal behavior starts. But still there is no liquefaction. Okay. Now let us continue with 30.98 degrees Celsius. Now let us come to 30.98 degrees Celsius. Okay, so when you go for 30.98 degrees Celsius, again you see what's happening. As you decrease the volume, the pressure is increasing, and when you reach a point where the pressure is 73 atmosphere, you will see that the gas has started liquefying, and some blue colored particles you will see. The liquefaction has started. So when the liquefaction of gas, see before above 73, I'm sorry, I'll change the color. Okay, at 30.98 degrees Celsius, above 73 atmospheric pressure, you see no liquefaction. Okay, but when you go for a temperature of 30.98 degrees Celsius, temperature is 30.98 degrees Celsius, you see the curve, the pressure is increasing with the decrease in the volume, but the volume decrease is less than increase in the pressure, and I come to the point where the pressure is 73 atmosphere. At this temperature, you see the liquefaction has started. Some liquid particles are formed. We have got liquid carbon dioxide. So at a pressure of 73 atmosphere, the liquid carbon dioxide is formed, means liquefaction has taken place. Liquefaction has occurred. So from here on, so from a pressure of 73 atmosphere, the liquid is going to be there. So from this point, that is this point to this point, if I say this is as E and this I'll say as H, so from point E to H, from point E to H, see from point E to H, from point E to point H, this is a liquid. So the liquefaction has started at E, that is at 73 atmosphere, when the temperature is 30.98. Okay, now when you still went down, when the temperature was still went down, you will see what happens here. From A to B, when I go to A to B, so here temperature is now 21.5 degrees Celsius. Okay, so here see at 30.98, and pressure of 73 atmosphere, the liquefaction has started. Okay, fine. So liquefaction takes place. So carbon dioxide liquefies at a temperature of 30.98 degrees Celsius and at a pressure higher or equal to, greater than or equal to 73 atmosphere. This is what he has found out. Still he went down to this temperature. Now see this temperature. Point A, 21.5 degrees Celsius, point A. So when I come from point A to point 5, point B, you see there is gas, but at point B, when the temperature is 21.5, the liquefaction has started. And you will see when I move from point B to point C, when I move from point B to C, there is liquid as well as solid. You will see liquid as well as solid. He found that there is liquid also and solid, liquid and gas also. So from point B to point C, there is liquid and gas, means the liquefaction has started at point G. See, at 30.98, the liquefaction has started at point E. And again up to point C, the liquefaction completes. So at point C, when the pressure is this much, see, pressure is not changing. From point B to C, pressure is not changing, but the volume is changing abruptly, and the liquefaction is completed at point C. And after point C, you see the volume is not changing to that much extent, but the pressure is definitely increased like anything. The pressure is increased, but the volume is not changing that much. The pressure is increased, but the volume is not changing to that much. At what? At 21.5 degrees Celsius. So between A to B, we have gas. Between A and B, we have gas. Between C and D, we have liquid. So that's what is there. Same logic is applied here also. Where for 13.1 degrees Celsius. See, for 13.1 degrees Celsius, what happens? Same thing again. We start at this point. Temperature is 13.1 degrees Celsius. So here, as I move from this point, I'll just come to I point. Before the pressure is So below pressure, where below P1 pressure, this is liquid, this is gas. This is gas. But after I to J, so when I move from I to J, when I move from I to J, okay, here again you will get liquid and gas. So liquefaction has started at point I at a pressure of P1. So at 21.5 degrees Celsius, liquefaction has started at pressure P3. At 30.1 degrees Celsius, the liquefaction has started at point where the pressure is P1, and so on. After J, after spot J, you see the volume is not changing that much, but the pressure is increasing like anything. The pressure is increasing like anything, but the volume is not changing that much. That means at this condition, after J, the liquefaction has completed. The liquefaction is completed, means liquid is completely formed. So here also we have liquid state. We have liquid state. We have liquid state. So on, if I just say these points, and if I join these points I, B, K and C, J, I get an area. That area would be like this, and in this area we found there is a liquid and gas. Above this area you have only gas, and towards left side you have only liquid. So this Andrews curve has given us an idea that the carbon dioxide is liquefiable below or equal to 30.98 degrees Celsius, and that too when the pressure is greater than or equal to 73 atmosphere. So at 73 atmosphere, what has started is liquefaction has started. This temperature and pressure are known as critical temperature and critical pressure. These are known as critical temperature and critical pressure, referred to as TC and PC. So critical temperature is the minimum temperature at which, see, it is a minimum temperature. Above that temperature you don't get a liquid, you will get a gas. So critical temperature is the minimum temperature at which, when you apply critical pressure of 73 atmosphere for carbon dioxide, the gas liquefies. So critical temperature is the temperature above which gas cannot be liquefied. The gas cannot be liquefied, however high the pressure may be. But below critical temperature, at a critical temperature or below critical temperature, if you apply the proper amount of pressure, it can liquefy. For example, for carbon dioxide gas, critical temperature is 30.98 degrees Celsius, critical pressure is 73 atmosphere. That means at temperature of 30.98 degrees Celsius, when you apply 73 atmospheric pressure to the carbon dioxide liquefies. Right? So here we have a curve analyzed completely, and that gives us an idea regarding what is critical temperature, what is critical pressure, and at a critical temperature and pressure certain gas particles are still existing because the liquefaction has just begun. Therefore it is volume can be determined as critical volume. So volume of the gas at critical temperature and pressure is called as critical volume. So we have come to the critical phenomena. Critical temperature, the temperature at and above which gas cannot be liquefied, however high the pressure may be. Critical pressure it is the minimum pressure require, it is a minimum pressure require at critical temperature. It's a minimum pressure require at critical temperature, so that the liquefaction begins, so it is called critical pressure. At critical temperature, the liquefaction has just, at a critical pressure, the liquefaction has just begun. So the volume occupied by the gas at critical temperature is known as critical temperature, and critical pressure is known as critical volume. So this is all about critical phenomena, liquefaction of gases. So here I have a gaseous state above, see 30.5, see this is a gaseous state, gaseous phase. You have a liquid phase, and in this dome shape, you have, in this dome shape you have what is known as the liquid plus gas. So here we have a temperature of 30.98, a pressure of 73 atmosphere, and the volume Vc, and this is called critical temperature, critical pressure, and critical volume. So that's all. The same logic can be applied to the other gases also, and you will see at a specific temperature or below specific temperature or above specific temperature, gas cannot be liquefied. So at that specific temperature, when you apply a certain pressure, the gas starts liquefying. That temperature is called as critical temperature. So at or below that temperature, if the gas is liquefying by applying pressure, then it is called critical temperature. At critical temperature, whatever minimum quantity of pressure you need to apply so that the liquefaction begins, that is called as critical pressure. And at critical temperature, there is still some gas remaining, and the volume of that gas at critical temperature and pressure is known as critical volume. So we have critical temperature, critical pressure, and critical volume. For carbon dioxide, critical temperature is 30.98 degrees Celsius, critical pressure is 73 atmosphere, and critical volume is to be found out. In my notes I have given you the list of all the critical temperatures and pressures for different gases. You can just go through it, and this completes the critical phenomena. To tell you the fact, this year's syllabus, this critical phenomena is not there, but you may require it for your competitive exam. Therefore I am explaining this critical phenomena. I hope you have understood this critical phenomena. Thank you. I'll stop here. We shall see the remaining things in the next video.